Welcome once again to the transistor lecture series, and in our previous lecture we have started the discussion on transistor biasing. So here we'll start our discussion on the first type of biasing, which is popularly known as fixed bias. So transistor biasing base resistor method. This method is popularly known as fixed bias. So the name itself suggests that there is a resistor connected to the base. So generally a high value resistor denoted as RB, generally of several hundred of kilo ohms, is connected between the base and the positive end of the supply of for PNP transistor, and for PNP transistor it will be the other way. So this is the circuit diagram for fixed bias, and we can see that there is a resistor RB connected to the base, and here positive terminal of the supply voltage. So if we see this, we can find that we need to find the value of RB entire process. So what happens here? Generally, the required zero signal base current is provided by VCC and it flows through the RB. Thus, the base emitter junction is now the forward bias. The required value of the zero signal base current, and as a result of the IC. So, IC we are denoting as beta IB, since ICBO is very small compared to IC. So beta IB, we can ignore that and directly we can assume that IC is equal to beta IB. Now it can be made to flow by selecting the proper value of the base resistor. Hence it is very much important to find the value of RB or choose the value of RB so that the collector current flows in the zero signal condition. So if this condition is satisfied, then we can proceed further in this particular biasing technique. Now for the analysis, let us first consider the input section. So this is the circuit of the input section, and here by applying KVL to this input loop, we can find that VCC minus the drop across these, that is IB RB, minus VBE, that is equal to 0. So this implies that IB is equal to VCC minus VBE divided by RB. So we can name this equation or number this equation 1, 2, and similarly our objective is to find the RB value. So we can say RB is equal to VCC minus VBE divided by RIB. So now it is important when we are designing a biasing circuit, base resistor biasing circuit or fixed bias circuit, we should have the information about the IB. That means we should have a goal to set IC, the output current, which is equal to beta IB. So if we have the knowledge of IC and if we have knowledge of beta, then we can set the value of IB, and once we set the value of IB, since beta VBE is a constant for silicon transistor, we know it is 0.7 volt, and for germanium it is 0.3 volt, and VCC also it is in our hand and we can make it fixed. So here we can easily find the value of RB, which is fixed in nature. So from the analysis of the input section, we can find that the supply voltage VCC and VB are constant. So thus the selection of RB sets the level of base current and hence the operating point also. Similarly, now if we analyze the output section and here already we have considered IC is equal to beta IB. So let us put a number to this relation also. Now here the interesting point that since the base current is controlled by the level of RB and IC, and it is related to IB by the constant beta, that means here constant beta and IB, these are relating to IC. Now the magnitude of IC is not a function of RC. So IC is not a function of RC. So it is a very important point that we should note, that the load, if we change RC value, if we change, IC is not going to change as long as VCC is same. So this is a very interesting point of the fixed bias. Now changing RC is not having any effect on the level of IC. As a result of it will not have any effect on IB. Now if we apply the KVL in this particular loop here, if we apply KVL, then what we find is VCC, that or VCC minus IC RC minus VCE, that is equal to 0. So from here we find VCE equal to VCC minus IC RC. So if we can fix RC, and due to the fixing of RC, IC is getting fixed. Even if we change RC, it is not having any effect on IC, but ICRC will change. So for a particular value of RC, VCE is not going to change. Now it may be noted that VCC is fixed, known quantity, and IB is chosen at some suitable value. Hence RB can always be found directly from these relations. So because of this reason, this particular method is called fixed bias. Now let us find the stability factor. So in earlier lecture, so if you have not seen the earlier video, I will put the link in the description box. Please go through that. So there we have derived this relation, stability factor is equal to 1 plus beta divided by 1 minus beta dIB by dIC. Now interestingly, in fixed bias method, IB is independent of IC, so that we can write dIB by dIC for fixed bias as 0. So here what we are getting, then this portion if we are getting as 0, then we can write S equal to 1 plus beta divided by 1 minus beta into 0. So S is 1 plus beta. So this is a very alarming thing. Stability factor is 1 plus beta. Now if we consider beta is 100, then stability factor is 101, which is quite large. Earlier we have seen that ideal value of S is 1. So up to 10, 15 S value may be considered, but 101 for beta 100, it is quite high, quite large. So this is providing poor stability for fixed bias method. Now there are some advantages of fixed bias method. So first of all, this is a very simple biasing circuit, only one biasing resistor we are using, and biasing conditions can easily be set and calculations are very simple. And there is no loading. Loading means the effect of mismatching of the impedance. So that loading condition is not there, because in the base emitter junction we are not putting any resistors. Now there are disadvantages also. So this method provides poor stabilization. Well, we have found the stability factor there, we have seen, and it is due to the fact that there is no mechanism to stop the self increase in the collector current due to the temperature rise and the individual parameter variation. So feedback mechanism is not there. And for example, if beta increases due to the transistor replacement, then collector current also increases by same factor as the base current is constant, because base current we have fixed on the basis of RB. Now stability factor, that is quite high, and therefore there are strong chances of thermal runaway. So because of these advantages, this particular biasing technique rarely used in the practical cases. So this is about the fixed bias method. So we end here this lecture. Thank you very much.